In August 2001, a telescope in Australia detected something that shouldn't exist. For less than 5 milliseconds, a burst of radio energy tore through the cosmos with the power of 500 million suns. By the time it reached Earth, it had traveled for billions of years across the expanding universe. The signal carried more energy in that fraction of a second than our sun emits in an entire day. Then, it vanished. No warning, no follow-up, just silence. For 6 years, scientists assumed it was a glitch, equipment malfunction, interference, anything but what the data suggested, that somewhere in the distant universe, something had unleashed an impossible amount of energy in an impossibly short time. What if I told you that we now detect these signals almost daily, that some repeat with eerie precision, that their properties violate our understanding of physics, and that their distribution across the cosmos reveals a pattern we cannot explain? Today, we journey through evidence that challenges everything we thought we knew about the universe's most violent phenomena. We'll examine signals that travel through space-time itself, leaving fingerprints that reveal the hidden structure of reality. We'll explore objects so dense that a teaspoon would weigh as much as a mountain. And we'll confront the possibility that what we're detecting might be artificial. The universe is sending us messages written in radio waves and cosmic catastrophe. Prepare yourselves. We begin. The discovery. The Lorimer burst. Duncan Lorimer wasn't looking for revolutionary discoveries in 2007. The astronomer at West Virginia University was doing something far more mundane, reviewing old data. His graduate student, David Narkovic, had been working through archival observations from the Parkes Radio Telescope in Australia, searching for pulsars, the rotating corpses of dead stars that sweep radio beams across space like cosmic lighthouses. On August 24, 2001, the telescope had recorded something unusual. Buried in data that had sat untouched for 6 years was a signal unlike anything in the catalogs. The burst lasted 4.5 milliseconds, less time than it takes to blink. But in that fraction of a second, something had released 500 million times the energy output of our sun. The signal showed a distinctive signature. Higher frequency radio waves arrived at Earth before lower frequencies, swept downward like a cosmic siren. This dispersion told Lorimer something remarkable. The signal had traveled through the plasma between galaxies, accumulating delays that revealed its origin. The mathematics were unambiguous. This signal had traveled 3 billion light-years to reach Earth. Think about that. 3 billion years ago, complex life on Earth was limited to single cells. Dinosaurs wouldn't exist for another 2.5 billion years. And somewhere across the cosmos, something happened that sent a burst of radio energy powerful enough to be detected across a third of the observable universe. Lorimer published his findings in 2007. The astronomical community reacted with skepticism. This had to be interference from Earth, satellites, radar, microwave ovens. Telescopes detect false signals constantly. Extraordinary claims require extraordinary evidence, and one unexplained blip in archival data didn't qualify. The burst was nicknamed the Lorimer burst. For most astronomers, it represented an interesting anomaly, nothing more. The pattern emerges. But Lorimer's graduate student, David Narkovich, kept searching. If one such burst existed in the data, perhaps others did too. Throughout 2008 and 2009, they found 4 more. Each showed the same characteristic sweep of frequencies. Each had traveled billions of light years. Each released staggering amounts of energy in milliseconds. In 2013, the breakthrough came. The Parkes telescope detected 4 more bursts in real time, not hidden in archival data. This eliminated the possibility of data corruption or processing errors. These signals were real, arriving at Earth as astronomers watched. Scientists gave them a name: fast radio bursts, FRBs. But the evidence forces us to confront an uncomfortable possibility. We had no idea what could produce them. Consider the energy requirements. A typical FRB releases as much energy in milliseconds as the sun produces in several days. Whatever creates these signals isn't just energetic, it's one of the most violent processes in the universe. And the bursts are fast, impossibly fast. Some FRBs brighten and fade in less than a millisecond, faster than any astronomical phenomenon known at the time. The mathematical constraints are brutal. If you want to create a radio burst that bright and that short, you need something extraordinarily dense and compact. The emitting region cannot be larger than the distance light travels during the burst. For a 5-millisecond FRB, that means the source must be smaller than 1,500 kilometers across. For comparison, Earth is 12,700 kilometers wide. The Sun is 1.4 million kilometers across. Whatever creates FRBs must be smaller than some asteroids, yet output more energy than stars. Only one type of object known to science fits those constraints: neutron stars. The neutron-star connection. A neutron star is what remains when a massive star explodes. During the supernova, the star's core collapses under its own gravity with such force that electrons and protons merge into neutrons. The result is an object roughly 20 kilometers across, about the size of Manhattan, that contains more mass than the Sun. The density defies comprehension. A teaspoon of neutron star material would weigh 10 million tons on Earth. That's equivalent to taking all the water in Lake Superior and compressing it into a sugar cube. The gravity at the surface is 200 billion times stronger than Earth's. The magnetic fields can reach quadrillions of times stronger than any magnet humans have created. These objects spin rapidly. Some neutron stars complete 700 rotations per second, turning faster than a kitchen blender at speeds that bring their equators to 15% the speed of light. Their magnetic fields interact with surrounding plasma in ways we're still trying to understand, creating conditions that exist nowhere else in the universe. If anything could produce FRBs, it would be neutron stars. But the problem was this: we'd been studying neutron stars for decades, and they'd never produced anything like an FRB. Pulsars, rotating neutron stars, emit steady radio beams. Magnetars, neutron stars with ultra-strong magnetic fields, occasionally produce X-ray flares. But millisecond bursts of radio energy with the brightness of FRBs? Never observed, never predicted. The theory seemed right, but the observations didn't fit. Then, in 2016, something extraordinary happened. An FRB repeated. 2. But this represents just one piece of a much larger puzzle hidden in the structure of space-time itself. Accumulating evidence. Observable signatures. The repeater. FRB 120202, discovered on November 2, 2012, by the Arecibo telescope in Puerto Rico. At first, it seemed like every other FRB, a single millisecond flash from a distance of 3 billion light-years, never to be heard from again. Except it did repeat, multiple times.
By 2016, astronomers had detected more than 150 additional bursts from the exact same location in space. This changed everything. If FRBs represented some cataclysmic event, like a neutron star collision or a black hole consuming matter, they should happen only once. Whatever FRB 121102 was, it could produce these incredible bursts repeatedly without destroying itself. The implications were staggering. This wasn't a death scream, it was a heartbeat. Scientists used multiple telescopes to triangulate the source's position with unprecedented precision. What they found deepened the mystery. FRB 121102 originated from a dwarf galaxy 3 billion light-years away, a small collection of stars that contained only 1% of the mass of the Milky Way. But this wasn't the strange part. The strange part was that the FRB source sat embedded in an extremely strong magnetic field, thousands of times stronger than typical interstellar space. The only environments in the universe with magnetic fields that powerful are found near supermassive black holes at the centers of galaxies, or around young magnetars. But FRB 121102 wasn't at the center of its galaxy. It was offset, sitting in a star-forming region on the galaxy's edge. Whatever produced these bursts was young, magnetized, and repeating. But the bursts themselves showed something even stranger: the downward drift. When scientists analyzed individual bursts from FRB 121102 in detail, they discovered an unexpected pattern. Each burst wasn't a simple flash, it contained structure. As each burst progressed over its millisecond duration, its frequency would drift downward in a specific pattern, like a cosmic slide whistle. The drift happened too fast for any ordinary emission process. Something was modulating the radio frequency on timescales of microseconds. The mathematics suggested the emission was coming from plasma moving at relativistic speeds, a significant fraction of light speed, in an extremely strong magnetic field. Scientists also discovered that the radio waves were polarized, meaning they oscillated in specific planes. And remarkably, the plane of polarization would rotate during each burst, sometimes completing nearly a full rotation in milliseconds. This phenomenon, called Faraday rotation, occurs when polarized light passes through magnetized plasma. The amount of rotation revealed that the signal was passing through one of the most extreme magnetic environments ever measured. But perhaps most intriguingly, the bursts showed what astronomers call sad trombones. The frequency drifted downward within each burst, at rates that suggested the emission region was moving or changing rapidly. Some bursts exhibited multiple frequency drifts stacked on top of each other, like cosmic overtones in a musical chord. These weren't random flashes. They were structured, complex, repeating signals emerging from extreme physics. The population explosion. By 2018, scientists had detected approximately 50 FRBs total. By 2020, that number had grown to several hundred. By 2025, astronomers detect multiple FRBs every single day. The explosion in detections came from a new generation of radio telescopes designed specifically to find them. The Canadian Hydrogen Intensity Mapping Experiment, CHIME, is a peculiar-looking instrument composed of 400-meter-long half-pipe antennas that scan the entire northern sky every day. Between 2018 and 2025, CHIME has detected over 5,000 FRBs. This flood of data revealed patterns that had been invisible before. About 3 to 5% of FRBs repeat. The others, the one-off bursts, might also repeat, but on timescales we haven't observed yet. We simply don't know. Scientists discovered that FRBs come in distinct populations. Some emit bursts across a wide range of radio frequencies. Others emit narrow-band signals. Some show complex spectral structure with multiple peaks. Others are simple and smooth. The repeaters tend to have narrower bandwidths and longer durations than the one-off bursts. Most remarkably, scientists discovered periodicity. Some repeating FRBs emit bursts in cycles. FRB 180916, located 500 million light-years away, produces bursts in a 16-day cycle, active for 4 days, then silent for 12 days, like clockwork. Another repeater, FRB 121102, shows possible 157-day periodicity. This was unexpected. What physical process could produce such regular cycles on timescales of days or months? Neutron stars spin in milliseconds or seconds, not days. Binary systems of neutron stars might produce orbital periods of days, but the bursts would still need to be explained. The evidence suggests something far stranger than anyone predicted. These aren't random cosmic accidents. They're structured, repeating phenomena with patterns we're only beginning to decode. Part B. Deeper implications. Mapping the invisible universe. FRBs have given us an unexpected gift. They let us weigh the universe. As these radio signals travel through space for billions of years, they pass through all the matter between their source and Earth. Every electron they encounter delays the radio waves slightly, with lower frequencies delayed more than higher frequencies. This creates the characteristic downward frequency sweep that helped Duncan Lorimer calculate the original burst's distance. The amount of dispersion, called the dispersion measure, is directly proportional to the number of electrons the signal encountered on its journey. And here's where it gets remarkable. By measuring FRBs from different distances and directions across the sky, astronomers can map out the distribution of matter throughout the universe. But when they did this calculation, they found something troubling. The dispersion measures were too high. Scientists had carefully counted all the visible matter in the universe, stars, gas clouds, galaxies, but the FRB measurements indicated there's approximately 50% more matter out there than we can see directly. This missing matter has been a problem in cosmology for decades. We know it should exist based on our models of the early universe, but we couldn't find it until FRBs showed us where it was hiding. The missing matter exists as warm, hot, ionized gas distributed throughout intergalactic space with temperatures around 100,000 degrees. It's too hot to emit much visible light and too diffuse to easily detect, but FRBs pass right through it, accumulating delays that betray its presence. By 2024, studies of FRB dispersion measures had confirmed the existence of this missing baryonic matter, solving a mystery that had persisted for 3 decades. But FRBs revealed something else too, something no one predicted: the local FRB. On April 28, 2020, multiple satellites detected a burst of X-rays and radio waves from within our own galaxy. The source was SGR 1935 plus 2154, a known magnetar located 30,000 light-years away in the constellation Vulpecula. The burst lasted 1.4 milliseconds. The radio component had all the characteristics of an FRB: the brightness, the duration, the spectrum. But this one was close, so close that scientists could study it in ways impossible for distant bursts billions of light-years away. For the first time, we caught an FRB in the act, and it came from exactly what theory predicted: a magnetar. Magnetars are neutron stars with magnetic fields up to 1,000 times stronger than ordinary neutron stars, quadrillion times stronger than Earth's magnetic field. These fields are so intense they distort the very atoms in the neutron star's crust, creating crystal structures that shouldn't exist. The magnetic pressure exceeds the matter pressure, making the star slightly non-spherical. And these fields are unstable. They evolve, twist, and occasionally crack the neutron star's crust in events called starquakes. When a starquake occurs on a magnetar, the sudden rearrangement of the crust causes the magnetic field lines to snap and reconnect explosively, like cosmic lightning. The event accelerates particles to near light speed, generating intense bursts of radiation. For most magnetar flares, this radiation emerges as X-rays, but in some cases, under conditions we're still working to understand, a coherent radio burst emerges instead: an FRB. The 2020 event from SGR 1935 plus 2154 proved that magnetars can produce FRBs. But here's what troubled scientists. The burst was relatively weak. If you scaled it up to the distance of typical extragalactic FRBs, it would be 100 to 1,000 times dimmer than the FRBs we detect from other galaxies. This means either our detection is biased toward the most extreme events, or magnetar flares exist on a spectrum, with some far more energetic than what we observed in 2020. Or possibly, the distant FRBs are coming from something even more extreme than normal magnetars. The cosmological distribution. As the FRB catalog grew, astronomers began analyzing their distribution across the sky and their distances. What they found was both expected and mysterious. FRBs appear to come from all directions equally. There's no preference for the galactic plane, no clustering toward the galactic center, no obvious association with nearby galaxies. This confirms they're extragalactic, originating from galaxies throughout the universe. Their distances span an enormous range. Some FRBs come from relatively nearby galaxies, 500 million light-years away. Others originate from the early universe, with their light traveling for over 10 billion years to reach us. One FRB detected in 2024, designated FRB 2022-0610A, had a dispersion measure suggesting a distance of over 12 billion light-years. We're seeing that galaxy as it appeared when the universe was only 1.5 billion years old.
But here's what's strange. When scientists compared the rate of FRBs across cosmic history, they found that the burst rate tracks the star formation rate of the universe. The peak of FRB activity coincides with the cosmic noon, the epoch 10 billion years ago when the universe was forming stars at its maximum rate. This suggests FRBs are associated with young stellar populations. Magnetars form from massive stars that explode as supernovae, and massive stars live fast and die young, existing only in regions of active star formation. The evidence fits. But some FRBs don't fit this pattern. Several have been traced to older elliptical galaxies that haven't formed new stars in billions of years. These galaxies shouldn't contain magnetars. All their massive stars should have long since died, yet FRBs emerge from them anyway. The evidence extends beyond simple magnetar flares into the realm of binary systems, neutron-star mergers, or something we haven't imagined yet. Act 3. The Big Picture. Part A. Theoretical Framework. The magnetar model. The leading theory for FRB production centers on magnetars, but with crucial additions. A magnetar alone isn't sufficient. The environment matters. Dr. Bing Zhang at the University of Nevada, Las Vegas has proposed a comprehensive model. In this framework, FRBs occur when a magnetar's magnetic field undergoes violent reconnection events in the star's magnetosphere, the region of space dominated by the star's magnetic field. These reconnection events accelerate electrons to near light speed, creating conditions similar to those in pulsar magnetospheres, but far more extreme. The accelerated electrons emit coherent radio waves through a process called curvature radiation, electromagnetic waves emitted when charged particles follow curved magnetic field lines at relativistic speeds. Under the right conditions, this emission can be amplified through maser action, where the radiation stimulates additional emission from other particles, creating a cascade that amplifies the signal to FRB brightness levels. But here's the key insight. This only produces an FRB if the magnetar is surrounded by a dense medium, a nebula of material from the supernova that created the magnetar, or matter shed by a companion star in a binary system. This material provides two things: electrons that can be accelerated, and ionized plasma that creates the dispersion and polarization signatures we observe. This explains why SGR 1935 plus 2154's burst was relatively weak. This magnetar is old, and the surrounding material has largely dissipated. Young magnetars embedded in dense nebulae would produce far more energetic bursts. The model predicts repeaters should show periodicity if they're in binary systems. The bursts would be more common when the magnetar's magnetic pole points toward material from the companion star. This matches observations of FRB 180916 and its 16-day cycle. But the model has problems. Not all observations fit cleanly. Alternative theories. Some FRBs show properties that challenge the magnetar model. The incredibly short durations of some bursts, less than a microsecond in a few cases, require emission regions smaller than 300 meters. That's smaller than the smallest neutron star. How can you emit an FRB from a region the size of a sports stadium? Dr. Konstantin Postnov at Moscow State University has suggested an alternative: collisions of neutron stars with asteroids or comets. When a massive object plunges into a neutron star's magnetosphere at high speed, the sudden injection of matter could trigger a burst of coherent radiation. This could explain the one-off FRBs. Each burst represents a separate collision event. But this model struggles to explain repeaters. What keeps feeding objects into the magnetar if bursts occur hundreds of times? Another theory involves supramassive neutron stars that exceed the normal maximum mass and are kept from collapsing into black holes only by their rapid rotation. As these stars lose rotational energy, they approach the threshold where they must collapse. The final moments before collapse could produce FRBs as the star's structure undergoes catastrophic changes. This explains why some FRBs come from old galaxies. A supramassive neutron star could exist for billions of years before finally collapsing, creating an FRB in a galaxy long past its star-forming days. The most exotic theory comes from Harvard astrophysicist Avi Loeb, who has suggested some FRBs, particularly the repeaters with unusual properties, could be artificial signals from extraterrestrial civilizations, possibly from light sails being propelled by powerful beams. The energy requirements and efficiency match what a sufficiently advanced civilization might create for interstellar propulsion. This forces us to reconsider fundamental assumptions about the signals the universe sends us. Are we observing natural phenomena, or could some percentage of these billions of bursts represent technosignatures, evidence of technology? Most scientists favor natural explanations, but the question remains open. The properties of some FRBs, precise periodicity, complex spectral structure, repeating patterns, don't rule out artificial origins. We simply don't know yet. Future implications. New instruments, new discoveries. The next generation of radio telescopes will transform FRB science. The Square Kilometer Array, SKA, currently under construction in South Africa and Australia, will be 50 times more sensitive than any existing radio telescope. When it becomes operational in 2027-2028, it will detect hundreds of FRBs every day, allowing scientists to build comprehensive catalogs of their properties. The Deep Synoptic Array, DSA 2000, planned for construction in the southwestern United States, will consist of 2,000 radio dishes working together to localize FRBs with arc-second precision, precise enough to identify their host galaxies immediately and study those galaxies in detail. This will tell us definitively whether FRBs correlate with specific stellar populations, galaxy types, or environments. But perhaps most exciting is the possibility of multi-messenger astronomy. FRBs emit radio waves, but what else do they emit? The 2020 Magnetar event produced both X-rays and radio waves simultaneously. Do FRBs also produce gravitational waves, neutrinos, gamma rays? Recent breakthroughs suggest yes. In 2023, astronomers detected coincident X-ray bursts with several FRBs, confirming that at least some produce multi-wavelength emission. If FRBs also produce gravitational waves, ripples in space-time itself, the LIGO and Virgo detectors might catch them, revealing the incredible violence of whatever creates these signals. Gravitational wave detection would be transformative. It would tell us definitively whether FRBs involve collisions, star quakes, or collapses. The gravitational wave signature is a fingerprint of the mass and velocity distribution of the source. We would finally know. Real-time alerts and follow-up. In 2025, astronomers have implemented rapid alert systems for FRB detection. When CHIME or another telescope detects an FRB, automated software localizes the source within seconds and sends alerts to observatories worldwide. Optical telescopes, X-ray satellites, and neutrino detectors all swing toward the source within minutes, searching for any accompanying emission. This rapid response has already yielded discoveries. Several FRBs show faint optical afterglows that fade within hours, too faint and too brief to have been discovered before real-time alert systems existed. These afterglows suggest that at least some FRBs involve significant energy release beyond the radio burst itself, possibly from shock waves propagating through surrounding material. The most tantalizing prospect involves using FRBs as probes of the universe's expansion. Because FRBs carry precise information about the matter they've traveled through, and because we can measure their distances through their host galaxies, they provide an independent method to measure the Hubble constant, the universe's expansion rate. This matters because current measurements of the Hubble constant disagree depending on the method used. Measurements from the early universe give one value. Measurements from the local universe give a different value. This Hubble tension suggests either our measurements have systematic errors or our understanding of cosmic expansion is incomplete. FRBs might resolve this. In 2024, initial studies using FRBs gave a Hubble constant value that falls between the two conflicting measurements, but the uncertainties are still large. As we detect thousands more FRBs with precise distance measurements, this uncertainty will shrink. By 2030, FRBs may provide the most accurate measurement of cosmic expansion ever achieved. We are using millisecond bursts from catastrophic events billions of light years away to measure how fast the universe is expanding. The implications are staggering. What this means for us? On a philosophical level, FRBs remind us that the universe remains deeply mysterious. Despite a century of modern astrophysics, despite satellites and telescopes studying the sky in every wavelength, the universe can still surprise us with entirely new phenomena. Before 2007, we didn't know FRBs existed. Now we detect them daily. They've revealed hidden matter throughout the universe, provided new methods to study cosmic expansion, and demonstrated that neutron stars are even more extreme than we imagined. But they've also humbled us. We don't fully understand what creates them. We don't know why some repeat and others don't. We don't know what physical conditions separate a quiet magnetar from one that produces FRBs. We don't know if all FRBs come from the same type of source, or if we're observing multiple distinct phenomena that happen to produce similar signals. Every answer raises new questions. Why do some FRBs show downward frequency drifts while others show upward drifts? What causes the periodic behavior in repeaters? Why do some bursts show multiple components stacked on top of each other? The universe is asking us to be smarter, to build better instruments, to develop more sophisticated theories, to remain open to possibilities we haven't imagined. And perhaps most profoundly, FRBs force us to confront the violence of the universe. These aren't gentle processes, they're among the most energetic events that occur. Magnetic fields that would tear apart atoms, gravity so intense that space-time curves noticeably, temperatures reaching billions of degrees, speeds approaching light itself. The universe isn't just vast and old, it's violent and energetic on scales we're only beginning to appreciate. And somewhere in that violence, in those impossible conditions, something produces signals that we, tiny creatures on a small planet, can detect and study. That's remarkable. That's worth celebrating. That's why we do this science. The ultimate questions. The nature of reality. The most profound implications emerge when we consider what FRBs reveal about the structure of reality itself. Space is not empty. Between galaxies lies a warm, hot plasma that we cannot see directly, but which makes itself known by delaying radio waves. FRBs have proven this medium exists, confirming a prediction from cosmological models. Space is filled with ionized hydrogen, the remnant of structure formation in the early universe, matter heated to 100,000 degrees as it collapsed into the cosmic web of filaments connecting galaxies. But here's what troubles physicists. The dispersion measures tell us how much free electron content the signals encountered, but they don't tell us how that matter is distributed. Is it smoothly spread throughout space, or does it clump into filaments and voids? Do the magnetic fields thread through it in ordered patterns, or are they turbulent chaos? By studying the polarization properties of FRBs, how the plane of polarization rotates as the signal travels, scientists can map the magnetic fields throughout intergalactic space. Early results suggest these fields are stronger and more organized than predicted, with field strengths around 1/1,000,000th of Earth's magnetic field persisting across millions of light years. Where do these fields come from? The early universe had no magnetic fields. They must have been generated later. But the processes that create magnetic fields on cosmic scales remain mysterious. FRBs are giving us the data to solve this. And then there's the question of space-time itself. Einstein's general relativity predicts that massive objects warp space-time, creating gravitational lensing, the bending of light around galaxies or galaxy clusters. We've observed this countless times with visible light, but what about radio waves traveling for billions of years through a universe filled with structure? Some FRBs should pass close to galaxies or clusters along their path, their radio waves bent and focused by gravity. This gravitational lensing could produce duplicate images of the same FRB arriving at Earth at different times, like cosmic mirages. We haven't definitively detected this yet, but theory predicts it must occur. When we finally observe a gravitationally lensed FRB, we'll be able to test general relativity in new regimes, radio wavelengths, milliseconds timescales, cosmological distances. If the lensing doesn't match Einstein's predictions exactly, we'll know something is wrong with our theory of gravity. The universe is offering us tests of fundamental physics. We just need to be patient and observant enough to notice them.
The repeater enigma. Let's return to the repeaters because they're genuinely strange. FRB 121102 has now produced over 1,000 detected bursts across a decade of observations. Some bursts are bright, some are faint. Some are narrow, some are broad. Some show complex frequency structure, others are simple. But here's what haunts astronomers. The bursts don't follow a predictable pattern. They cluster in time, periods of intense activity followed by weeks of silence, but the clustering itself isn't periodic. It's quasi-random, suggesting the physical process triggering the bursts has some stochastic element. One possibility involves magnetar starquakes that occur unpredictably as the ultra-strong magnetic field stresses the neutron star's crust. Another involves accretion. If the magnetar is pulling material from a companion star, variations in the accretion flow could trigger bursts sporadically. But FRB 180916 complicates this picture. Its 16-day periodicity is too regular to be random starquakes. Something must be modulating the burst activity on that precise timescale. The leading explanation involves a binary system where the magnetar orbits another star every 16 days, with bursts occurring preferentially when the magnetar's magnetic pole points toward the companion's stellar wind. This works mathematically, but we haven't detected any companion star yet. Optical telescopes have studied FRB 180916's host galaxy in detail, but the source is too distant and too faint to resolve individual stars. We need better spatial resolution to confirm this. The most disturbing possibility is that we're observing multiple different physical processes, all producing FRB-like signals. Some repeaters might be magnetars and binaries. Others might be isolated magnetars with active magnetospheres. The one-off bursts might come from collapsing supramassive neutron stars, or neutron star-asteroid collisions, or binary mergers. We might be grouping together fundamentally different phenomena based on superficial similarities: short duration, high brightness, radio emission. It would be like classifying both lightning and nuclear explosions together because they both produce bright flashes. They look similar, but the underlying physics is completely different. Only more observations will tell us if FRBs are one phenomenon or many wearing similar masks.
The artificial hypothesis. We must address the possibility that some FRBs could be artificial. Avi Loeb's hypothesis about light sails powered by directed energy beams is scientifically legitimate. If an advanced civilization wanted to accelerate spacecraft to significant fractions of light speed, one efficient method would be to push them with powerful beams, perhaps in radio wavelengths. From Earth, we would detect these beams as brief, intense bursts of radio energy. The hypothesis makes specific predictions. Artificial beams would show different properties than natural astrophysical sources. They might exhibit regular spacing if multiple spacecraft are being launched in sequence. They might show Doppler shifts corresponding to acceleration. They might align with habitable star systems. So far, no FRB has shown properties that demand an artificial explanation. But, and this is important, we haven't ruled it out either. The data are consistent with natural magnetar flares, but they're also consistent with directed energy beams for propulsion. The most we can say is that if FRBs are artificial, they're being produced by multiple civilizations across the universe, because FRBs come from galaxies in all directions and at all distances. That would imply advanced civilizations are common, which contradicts the apparent emptiness of the cosmos, the Fermi paradox. Unless the civilizations are there, operating on scales and timescales we don't recognize as technological. unless intelligence in the universe doesn't look like humans with radio telescopes, but something stranger, civilizations that harvest the energy of magnetars, or engineer neutron stars, or manipulate space-time itself. The evidence doesn't point toward this, but the evidence doesn't exclude it either. And in science, we must remain open to hypotheses that fit the data, even if they challenge our assumptions. The universe might be sending us messages. We're working to decode them, and we must be prepared for the possibility that the answer, when it comes, will be stranger than any of the scenarios we've imagined. The cosmos is vast, the mysteries are endless, and somewhere in the radio spectrum between the frequencies of hydrogen and helium, signals flash briefly across space-time, carrying information we're only beginning to understand. We're listening. That's what makes us human. We detect, we analyze, we question. We reach toward understanding even when the universe responds with questions instead of answers.
The FRB mystery isn't solved, it's deepening. With every new detection, the picture becomes more complex and more wondrous. And that's exactly how discovery works. Conclusion. We began this journey with the question: what causes these impossibly bright, impossibly brief flashes of radio energy from across the cosmos? We've examined the evidence. Neutron stars pushed to their limits, magnetic fields that shatter the very crust they emerge from, signals that travel for billions of years through space-time, accumulating delays that reveal the hidden structure of the universe, repeaters that flash with mysterious periodicity, bursts that carry more energy in milliseconds than our sun emits in days. We've seen how FRBs revealed the missing matter between galaxies, confirmed magnetars as plausible sources, and raised new questions about periodicity, emission mechanisms, and cosmic distribution. We've explored competing theories, starquakes, binary systems, collapsing neutron stars, and acknowledged we don't yet know which is correct. We may be observing multiple phenomena, all producing similar signals through different physics. The current scientific consensus is that most FRBs originate from young magnetars in dense environments, with their magnetic fields undergoing violent reconnection events that accelerate particles and produce coherent radio emission. But significant mysteries remain: the on-off bursts, the ultra-short durations, the complex spectral structure, the periodicity, all demand explanations we're still developing. What we've learned is this: the universe remains far stranger than we imagined even a decade ago. Before FRBs, we thought we understood neutron stars fairly well. Now we know they're capable of phenomena we never predicted. Before FRBs, we assumed the space between galaxies was effectively empty. Now we know it's filled with hot, magnetized plasma that shapes how signals propagate across cosmic distances. Every answer reveals deeper questions. Every solution opens new mysteries. That's the nature of science. We don't move from ignorance to complete knowledge. We move from simple questions to more sophisticated ones. The universe is sending us signals: brief, bright, powerful, mysterious. They carry information encoded in their frequencies, their polarizations, their arrival times. They tell us about magnetism, gravity, plasma physics, cosmic expansion. They reveal both the violence and the structure of reality. And we're listening. With larger telescopes, better algorithms, faster computers, more sophisticated theories.
The FRB mystery will be solved, eventually, perhaps within a decade, perhaps within a century. The answer will likely involve physics we understand, combined in ways we haven't imagined. It might reveal new states of matter, new plasma instabilities, new forms of stellar evolution. Or it might confirm what we already suspect, that magnetars are even more extreme than we thought. But whatever the answer, the journey will have been worth it. Because in seeking to understand these signals, we've mapped the invisible universe, tested fundamental physics, and pushed the boundaries of observational astronomy. We're small creatures on a small planet, detecting whispers from across billions of light years. Those whispers tell us we're part of something vast and ancient and extraordinary. The universe speaks in radio waves, in gravitational waves, in light and neutrinos and cosmic rays. We're learning its language, and every message, every signal, every flash from the void reminds us why we look up. The universe is vast, the mysteries are endless, the journey continues.